Okay, so we explained the structure of one of these little repeating units, one sarcomere. And now let's start thinking about what the behavior of a muscle would be if you had these sarcomeres stacked up end to end. We'll cover this in a future video, but one of these strands of sarcomeres stacked up end to end is something we call a myofibril. Myofibril. Not to be confused with a myofiber, which is many of these in parallel. So myofibril, that's one of these units of sarcomere stacked end to end. So you can make an argument from simple physics that the amount of force produced by a myofibril can only be the same as the force produced by one sarcomere, right? Because it's like a weakest link in the chain argument, that if a myofibril produces a force of, say, 3 newtons, each individual sarcomere must, on average, be producing that amount of force, correct? So that's useful to know. It means we can treat an entire myofibril just as a scaled-up version of one sarcomere. So if there's, say, 500 sarcomeres in a myofibril, we can just say it's a sarcomere that's 500 times as long and has exactly the same force production capabilities. So what about myofibers? What about this situation where, say, let's focus on this part right here. So what's going on here is probably we have, like, here's one myofibril, here's another one, here's another one. They're all stacked up in parallel. Well, that means that's like, well, here's like 2 myofibrils stacked up in parallel, one like this, and of course there'd be many more in an actual muscle fiber, but when we stack these up, that's just a muscle fiber. Well, not 2, but many myofibrils in parallel. So one thing you can do is you can take a muscle fiber, and if you look at it, like a cross-section of it, you can see that it's made up of little myofibrils stacked up like a fistful of pencils or something. So now we talked about how these sarcomeres in series, so like this one and this one, they all on average have to be producing the same amount of force. How much force could a muscle fiber produce? Probably the sum of all the forces, right? Because if this one's producing like 3 newtons and this one's producing 2 and this one's producing 1, and be 3 plus 2 plus 1 is 6 newtons, you just add them up. So that suggests something very interesting. It suggests that muscle fiber strength, and let me write this out, fiber strength is going to be proportional to, I'm using this proportionality symbol, maybe you've seen in math class, the cross-sectional area of the fiber. Maybe I'll just write fiber cross-sectional area. Because if you have more of these fibrils, maybe my muscle, one of my muscle fibers looks like this, but yours has some more fibrils in it, you're going to be able to produce more force, right? But of course, they'll take up more space. So, bigger cross-section of muscle fibers, more force. There is actually a very tight mathematical relationship between the cross-sectional area of muscle and the amount of force you can produce. And there's a term for this. This, you should know, this is called the specific tension. One of those funny engineering words. And again, this is something you estimate from experiments, and so there's a range of uncertainty around it. It tends to be between 30 and 60. The units here are newtons, which is unit of force, per centimeter squared. So maybe on a problem set, I'll have you convert this into, say, like pounds per square inch. But presumably you know how much a square centimeter is, 1 by 1 centimeters. And, well, let's see, 60 newtons would be about 15 pounds. So that means roughly that 1 square centimeter of muscle can produce about 15 pounds of force, which, roughly seems about correct. So if you know the cross-sectional area of a muscle, you should be able to scale up the strength of an individual sarcomere to whatever the cross-sectional area of the muscle is. Now, there's one complicating factor, and here it is. You should be able to add up the individual sarcomeres, like their individual contributions, with a cross-sectional slice of the muscle fiber. But the cross-sectional slice of the muscle fiber does not necessarily correspond to the anatomical cross-section of the muscle. Let me show you what I mean. So that cross-sectional slice I just showed you on our model of muscle right here, our very simplistic model of muscle, is not like this. It's like this. It's technically perpendicular to the muscle fibers. So it's this area that affects muscle strength, not, say, this cross-sectional area, which is like if you measured the circumference of your calf muscle, you might measure it like this as opposed to this. Now, the difference between them is dictated by something we encountered last week, which is this angle right here, meaning the angle between the orientation of the tendon and the orientation of the muscle fibers. So maybe we'll just use lowercase phi for that for now, because I think that's what's in the notes. And that's called the pennation angle. So the fact that this pennation angle means that it's this area we care about, not this area. Maybe if I use an example on my skeleton here, it will be more clear. This muscle right here, we care about that slice, perpendicular here, not, so that as opposed to that, if that makes sense. Now this gives rise to a concept called the physiological cross-sectional area. And I'm going to spend the whole next video talking about that in detail, but I wanted to show you where that idea comes from.